when a student comes to you, right, and he is, let's say, interested in quantum and has read a little bit about quantum and he knows something and he has some questions. So there are some basic theories of quantum, like that slit experiment, things do not exist, and all those kinds of things. Whatever little knowledge I have gathered, I'm just sharing. You are the professor. So now you explain to me what are the basic theories of quantum in a simple language for our viewers, two or three theories that are there. If you can explain that.
Okay, great. So if I have to start with the quantum, we have to understand that quantum mechanics itself is a framework. Okay, it's a framework where you want to know the properties of some quantum particles, so very elementary particles. Okay, so that Sudip, I would say that you really have to know the difference between this. To appreciate quantum mechanics, again, I would say that you have to know the difference between the classical mechanics and the quantum mechanics. For example, when we talk about the classical mechanics, or when you, classical mechanics is um, all about the phenomena what you see in the macroscopic world, or how the body behaves in the macroscopic world. Okay. For example, in classical mechanics, the object which we speak about, whether it's a chair, it's a table, it's a laptop. Okay. Uh, so the properties that possess, whatever properties that objects possess, okay, is is there. Irrespective of any measurement. You have to understand that. Whether you measure it or not, let's say this piece of mouse will have a mass, because every body is made of a matter. Okay, this is a macroscopic object, but in quantum world you are not able to see the things. Okay, in the quantum world the electrons are so tiny things you cannot even hold it. So when you cannot see the things, when you cannot hold the things, how can you explain the things? Okay, so that's the thing. So that's the difference between the classical mechanics and quantum mechanics. In quantum mechanics, uh, when you don't see a thing, it does not possess any property. Although, irrespective of the measurement, until you do the measurement. Okay, for example, the electron, whether it is spinning in clockwise direction or anti-clockwise direction, you will never know until you measure the thing. Okay, but the color of this mouse, whether you see, I see, she sees, or whoever sees, is always black, isn't it? Okay, so this is the main difference between the quantum mechanics and the classical mechanics. Another important thing is that when we are talking about these elementary particles, okay, there, these quantum particles, the world of quantum mechanics is totally, it has an inherent fuzziness in this system, in this quantum universe. Okay. For example, there are many things, even in the past, people have found, for example, uh, Max Planck. Okay. Max Planck in the year 1900, he came up with the idea, actually, he coins the word quantum first. Okay. So how did he come, or how did he brought this subject? Okay. Earlier it was just Newtonian mechanics or other mechanics. Okay. But not electrodynamics was there. Okay. These were very old. But the quantum mechanics is something which came in this 1900. Okay. So what Max Planck has observed in his experiment is that he was doing spectrum studies on black body radiation. Okay, black body is something which can absorb or emit any amount of, or any wavelength of light. So then what experimentally he's observed is that uh, uh, that when the wavelength, or when the frequency increases, frequency of the emitted spectrum increases, the intensity drops. But in classical mechanics, you don't see the drop. Classical mechanics says that when you increase the intensity, or when you increase the frequency, the intensity will increase, or it can go to infinite. But then experimentally, he found that no, it's not going infinite, it's dropping. Okay. Then he came up with the theory that the emitted electromagnetic spectrum from the black body is basically comes in a discrete form of packets called quanta. Okay, so you see, I mean, again, for him also, he wanted to explain the things from the knowledge which he had, but then something did not fit up. So then he formulated a new formalism or new theory, which is called the quantum theory. Okay, the similar thing happened with many other people. I mean, as you took a example of the double slit, Young's double slit experiment. Before Young's double slit experiment was, he actually wanted to prove, or he wanted to show the wave nature of these electrons. Okay, I will come to this part. I mean, there were, I mean, certain revolutions took place around 1920s, which came up with many interesting ideas. For one of the idea was elementary particle can behave both as a, or elementary matter can behave both as a particle and wave. Okay, but yes, he did his experiment. I believe he did his experiment in the year 1870. I believe Young's double slit experiment. Okay, but he wanted to show the wave nature of those wave nature of the light. Okay, but before that, some corpuscular theory came up. Okay, corpuscular theory said that photons, not photons, the light is basically made up of tiny particles which travels in straight line and so on. So, okay, so science is indeed kind of a baby steps. Okay, to establish one, or to establish the foundation of quantum mechanics, it never happened overnight. People from 17th century, people from even 16th century, they started Dalton. Okay, Dalton came up with the idea of the atom. Okay, so these are all quantum particles, and we see the journey. Okay, so I mean, quantum is a very, it's a very interesting thing, and only due to the fact that you are not able to see the elementary particles. Okay, and as a result, in the year, I believe, Louis de Broglie, Schrodinger, Heisenberg, these are the very famous scientists that came in the year around 1925, 26, 27, back to back. They gave a solid foundation of quantum mechanics that if we are now satisfied that all the elementary particles indeed behave as wave also, then let's formalize a new mathematical treatment how to represent such waves in quantum mechanics. Okay, and this is how the story went on. Okay, so now you can deal electron as a particle, which Einstein did. Okay, Einstein, what was the Einstein's experiment? His 1905 paper on photoelectric effect. Okay, it was basically he tried to extend the idea of Max Planck and incorporate his work. And later he found that, or he concluded that photons or those lights are made up of tiny elementary quanta particles called photons. Okay, so you shine the light on a particular material, and from that particular material, those electrons will come out, and then those electrons can be used to conduct electricity. Okay, or photocurrent. But again, you see Einstein's actual photoelectric effect. I mean, he gave the actual um, theoretical explanation of photoelectric effect. But then, way before Einstein, there was a scientist called Heinrich Hertz. Okay, Heinrich Hertz was the first one who actually observes the photoelectric effect. Okay, and he saw that the sparks that is coming out from the zinc plate, where he irradiated the zinc plate with the UV light, some sparks starts coming up. Okay, and at that time, quantum mechanics was not known to anyone. But luckily, Einstein took his work and then repeat the experiments, and then he explained successfully. And then later he came up with the fact that the light which we are indeed see is basically a quanta of particles, okay, which is called photons. Okay. So quantum world is very different world, Sudhi. I would say that, as you asked me that how do you explain to a normal students or normal any normal person from any background of life, I would say that you can take an example of, let's say, a bus. Okay, a bus on a road. Okay, if you know the position of the bus, if you know the velocity of the bus, you can 100% says that at what time the bus will reach to your home or at what time the bus will reach to your office. Let's say if the bus does not break down or if the bus does not, experience any hardware problems. Okay, but in quantum mechanics you cannot do that. Okay, because it's a wave which you cannot hold. Okay, so quantum mechanics says that it's all about probabilistic. It's a probabilistic approach. Classical mechanics is more deterministic approach. You can determine exactly when the bus will reach. But in quantum mechanics, it's a wave approach which can probably tell you that where the particle is. It cannot tell you exactly where the particle is. Okay, here comes the picture of the Heisenberg. Okay, Heisenberg actually gave the same thing. Okay, Heisenberg's paper, Heisenberg was known for, he was known for two things. One was he developed the quantum mechanics in a matrix form, and the other part is the Heisenberg's uncertainty principle. We had been reading these Heisenberg uncertainty principles ever since we were in class 9 standard or class 10 standard. Okay, maybe little one sentence was there, and in 11 standard or 12 standard, more broad sentences were there. Okay, so Heisenberg uncertainty principles clearly state that you cannot measure the electron's position and the momentum of the electron simultaneous. Okay, as it, you can relate these things with the classical world. For example, in the fair, you might have seen people blowing bubbles, right? You might have seen people blowing bubbles. Okay, if you try to catch the bubble, okay, the more you try to go towards the bubble try to fly away. Okay, so that's the thing. Okay, so quantum is something which is already present in the nature. Okay, so Heisenberg uncertainty says that when you try to determine the positions of the electron accurately, you basically lose control of the momentum of the particle. Okay, and there was indeed one experiment. There was a tiny hole made in a plate, and on the other side of the hole, you flash a light. You flash a light from the hole through this hole, and then you will indeed see that it's just not a spot on the screen which is coming up. Rather, it's a kind of a broad, delocalization of the waves. Okay, but again, you see in the classical picture, if I have a gun and if I shoot the gun from through this hole, okay, you can 100% say that this is the area of the wall which will get affected by the bullets. It's the same area as the area of the hole. But in the quantum mechanics, if you shoot an electron through this hole, okay, it's just not only on that center spot, you will also have some patterns on the sideways. Okay, both right and left of the central portion. Okay, this is what quantum mechanics is. Okay, you cannot explain these things with the help of simple classical knowledge.